It's like I'm directing now while I produce the video here. All right. If you are watching the video, before you do anything else, stop and jot down some notes about what you know about extreme values of functions and the behavior of a graph around them. Before you listen, aka cheat by listening to our conversation about it, do that now. All right. So, what did you come up with, gang? Jacob, why did you move further away? That was a rhetorical question. All right. What's the matter, Aaron? You look confused. Okay. I'm just a confused person. Life confuses me. What did you come up with about what happens? Okay, give me one case of an extreme value. A maximum. Okay, what happens at a maximum? It's the highest point. So, what do we know about the function behavior, say, to the left and right of it? The function has to increase coming from the left and then decrease to the right. Yes? Okay. How about, what's the other kind? Minimum. And so what happens there? Decrease to it, increase away from it, right? What about the difference between, or no, let me make a statement, and I'm going to kind of test y'all this way. If I tell you that I found a maximum value at 3 for a function. Now, and this is something teenagers are terrible at. You have to take what I said exactly as I said it. Does that mean that that is the highest point on the entire function?
No.
Why not?
Because it could be on an interval.
That's exactly right. See how much y'all already know? We're just going to put the calculus to what you just said. Okay? So that proves that, in fact, some groundwork has been laid. All right, so let's start with a definition. Now, I'm going to put an additional word in here, which is also a heading in your book, but I want you to understand that the word absolute can also be stated as the global, and that's a G, the global extreme value. So the absolute or global extreme value is the absolute highest or absolute lowest on the entire function. Okay? Name a function that you know has one of those. Like a parent function. X squared, sin x, absolute value, right? These are all graphs that have absolute maxes and mins, right? Okay. So, let f be, I know I'm writing big, it's okay, because I'm only going to put this on the screen. Let f be a function with domain, if that could make words, add letters there, domain D. All right. Well, why would it make sense that this definition would have to have sort of two pieces to it? If I'm defining absolute global extreme values, and I think I left the S off of values, so I'll fix that now. Why would it make sense that this definition would need to come in parts? I will give you a hint. It relates to what we just said.
Because the absolute values must exist on like a certain interval.
You're making it harder than it is. That's right, because we have to talk about maxes and mins separately because the behavior around the graph of those two is the opposite, right? Okay. And that's not like a big deal either way, whether that made sense to you, but all right, so, and I'm going to abbreviate, and it's probably bad. If the English teacher was here, she'd probably slap my wrist, or he, Miss Goodwin. And see, again, I will tell you that what would frustrate English teachers if they came into my classroom, which I think they would understand why we do it, but what would frustrate English teachers about the way I have you write is that I'm teaching you how mathematicians and scientists write. If they're writing an explanation, they won't necessarily put it in words, like full words and proper grammar and all that, because what matters more is that the meaning of what they're saying is conveyed. Okay? So obviously when you write anything, the meaning is very important, but in math, or science, we want it down to where we can write quickly and summarize, succinctly what's happening, okay? So this is your universal notation and wording, and you can express it this way onto the AP exam, and people will understand what you're saying, okay? So the absolute max value. Okay? So this is an extension of a sentence that comes back up here to the top. So let f be a function with domain D, then f of c. Now I'm pausing there because I didn't want to sidetrack us from the bigger idea here, and we're going to come back to this. What does f of c mean? The function value at c. All right, if we're talking to an Algebra 1 student, how will we explain that to them? If I have a point, where's my f of c? It's the y, right? So it's the y coordinate, it's the output. When? Yes, x is c. Well said, Will Condor of the haircut. Looking sharp today, sir. Okay, maybe you should get your haircut every day. No, I'm just kidding. Okay, then f of c is the, did y'all get it? Sharp. God, y'all are a tough crowd. All right, so the A part of the definition is then I'm going to read the sentence to you so it makes sense. Then f of c is the absolute maximum value on D. And what is D? On the domain. So in other words, everywhere for the function, right? Now, I believe I've used this with you before, but I'll reiterate it if I need to. What does that mean? If and only if. Yes. If and only if f of x is less than or equal to f of c for all x in D. So what does that say? Translate that into words that, I don't know, an Algebra 1 student would understand. Okay, but there's an if and only if there. But what did he leave out? And he's not wrong. He said f of c is the greatest y value. That's true. Right, on the domain of the function, right? And for an Algebra 1 student, what would that imply? It's the highest point on the entire thing, right? Does that make sense? Okay. All right. When would an x squared or an absolute value have an absolute maximum? But when would it? Okay, let's back up a step. For x squared and the absolute value graphs, which are the most obvious examples of extreme values, that makes sense? Okay. When would my extreme value, well, first of all, what is the extreme value for the parent? A max or a min? Min. When would that min become a max? That's right, if you have a negative leading coefficient, right? And what do we call that in function transformation land? Negative a, right? Y'all with me? Okay, so then we go to B, and I'm just going to write the words, and then I want you to tell me what the definition should say. So let f be a function with domain D, and I'm reading the preface to you to remind you of what these extensions mean. Then f of c is the absolute minimum value on D if and only if, what has to be true there? Okay. Now, just to make sure that the microphone picked that up, I'm going to repeat it. F of x is greater than or equal to f of c for all x in D. Now, if you've been with me, especially since last year, this should be obvious, but I try to stop and do little things like that with you to help get you more comfortable with reading, symbolic notation and that sort of thing, because in college you'll be doing a lot of that, and your professors will fly through it and you'll think, I must be the only one in the room that has no idea what he just said. But you get good at writing it down and coming back to it later, and the trick is to take it piece by piece like we just did and understand it. Does that make sense? So I'm not trying to just teach you calculus. I'm trying to get you ready. All right. And I'm just going to put a little quick note here because there's a lot of terminology here, and I sort of laugh and cry at your amazement at certain words. Like, what is that? And I'm like, really? You don't know that word? Okay. So what does global mean? Worldwide. Like, so in math sense, that would be like, this is going to be true everywhere, right? Okay. And if it's a global match for a function, that would imply it's the highest point on the graph everywhere, right? If no matter, there's nowhere else on the function where the function attains a higher y value. Does that make sense? Okay. Well, one extreme, two extrema. So make yourself a note. This is simply the plural of extreme. I'm going to repeat that because the microphone might not have picked it up. Ryan Kelly just said, thank God Trace is not here. I know he will. That's why I repeated it. Because he would tell me later, that would have been so funny if you had put that on the video. Now he can laugh because I did. All right. So, the screen is driving me crazy. It gets smudges on it, and then the pen gets caught in the smudges, and it's bad. That's when I suddenly look like I can't write, because I'll hit little smudgy spots and it starts making little sticks instead of letters. Either that or Preston is using mind control to take over my hand. Just kidding, Preston. Love you, mean it. And can I just give a shout out to Connor? Connor, I was super proud of you last night grading your test. I just have to tell you that. I know. Maybe he should have been repping earlier, like in pre-cal. Okay. And then he wouldn't have had to be forced to stay in calculus. The Lord works in mysterious ways, Connor. All right. I'm going to go ahead and put the abbreviation up here because this is how we will refer to this theorem. But in the context of what we just said and the fact that it's a theorem and theorem starts with T, what do you think this theorem is called? It is the extreme value theorem. Okay? So if you need to make yourself a note of that, I will pause and let you, but I'm not going to write it up here. Okay? And I just had a great little moment I have to share with you because you wouldn't have seen this because you don't have my vantage point. I just looked back and Chance was laughing wearing his shirt. I found this humorous. It was funny. Kind of like when my daughter called me as I was getting into the car last night and the sunset was incredibly, I don't know if you saw it last night, but when I was leaving, and I have a picture I can show you later, because I'm a sky freak, I took pictures of it. The sky, when I first went out, was like really sharp pink, like down at the horizon. So I took a picture of that, and I put some stuff in my car, and literally, like, this was probably 20 seconds later. I looked up, and it was like red, brilliant red, so I took a picture of that too. Yeah, and as I took that picture, my daughter called, so I was like, it's awesome. All the angels got together at once. All right, the theorem says, now, what is the structure of an if-then statement? How do if-then statements work? Okay, yeah, it does start with an if. Okay, let me give you something you may have heard from your parents before. If you wash the car Saturday morning, then you can do whatever it is you just asked to do, right? Okay, that's an if-then statement. So how does that work? That's right, it's conditional. There's a condition there. You have to meet the condition. Well, now using a parenting example is bad because I've heard parents say that and then turn right around and completely ignore what they just said. I'm like, you just told your child that it doesn't matter what you say. It's just whatever whim you're feeling at the moment that somebody actually asks you something. All right, but if we go by the rules of logic and I give you a conditional statement, why is it called a conditional statement? Right. Whether or not you get the conclusion depends on what, Todd? Yes, that's what I thought. Maybe I should bring you up here.
No, he was talking about
seating chart in my head, Todd up front. Yes, this will happen. Okay. So don't feel sorry for him. Todd is the last person on the planet who needs someone's sympathy. Todd needs someone to smack him out of his senselessness into sense. So don't slap the senselessness out of him, not slap the sense out of him. So, in order to get the conclusion, I have to meet the condition, and the condition occurs where in the statement? At the beginning, in the if part. All right? Now, I say that because this is a very important theorem. Okay? And there are several of these that I will highlight for you as we get to them throughout the course that you need to know, because if the directions say, let's back up a step. Just like if I said use the definition of continuous to prove, and you did anything else, you get no credit. Because the question is not testing whether you know how to use other means. It's designed to determine whether or not you in fact know how to use the mean assigned. Okay? So the means here would be use the extreme value theorem to determine whatever. Okay? So here's the if part. If f is continuous. Now I'm just going to pause right there. Or no, let me go ahead and extend that. On a closed interval. And the book uses the words, but I'm just going to write bracket A, comma B, bracket. Because that's how we denote a closed interval, right? And to me it's redundant when we say on a closed interval, bracket A to B, bracket. All right? So that's my condition. So if I give you a function with a discontinuity on an interval, and I ask you to reach some sort of conclusion about it, can you apply this theorem? No, you cannot, okay? This is pretty cool, though. Then f has both a max value, and I'm abbreviating max val, and min val on the interval. Now let's look at some pictures here, and I want to sketch you some scenarios. Because that sort of seems impossible, but let's think about it this way. If you imagine any function you want to, okay? And any section of that cubic. Somebody said cubic, so pick any section of whatever function you chose, okay? Picture that in your head. Now, does yours have a max and a min? Why?
Because it stops.
Yeah, because if I close the interval, it's like I cut out a piece of the function. So if nothing else, let's just say if I took, and I'm going to do a little bit different pictures than I did the book, but let's just say we took a parabola, and I took that little piece of it right there. Where is its maximum? And those are closed endpoints. I'm not taking the time to draw those in, but we're understanding that this is examples of what we're talking about. All right? Where's my maximum? At the right endpoint. Okay? Where is my absolute minimum? It's at its vertex, right? Okay? Well, if I have something like this, there's a little more going on. What about this situation? The absolute maximum occurs at the top peak, and the absolute minimum occurs at the bottom dip, right? Now, but notice the distinction in these two. Where did the maximum occur on the first one? At an endpoint. The minimum occurred at a low point, right, in the interior. Now, notice in the picture I just drew, where would my absolute maximum and my absolute minimum occur? Both at extreme values, right? So what kind of sense do you have right now just looking at those two pictures where those maximums and minimums will occur? Either where or where? At an endpoint or at a peak or a dip, right? And that's a very hard and fast, simple rule to go ahead and establish for yourselves now. That's the way it's always going to be, okay? obviously, if I had something like this, like a little piece of, say, an exponential graph. And what kind of exponential graph would this have to be? Decay. Okay. How can you get decay in an exponential graph? A negative exponent or a positive exponent. When do I have decay? When the base is between 0 and 1. Right? Okay. And the presumption when you're talking about exponentials is that your base is always positive. Okay? So, what about this guy? This little chunk I just drew. If we agree that this is a rough sketch of a chunk of an exponential graph, where are my max and min? At endpoints. Is there any piece of an exponential graph that I could choose where that would not be the case? Why not? Because all exponential functions are either blank or blank everywhere. Increasing or decreasing, right? So if I take some little snippet of it, it can't violate that rule. Does that make sense? So what else do we know about exponential graphs that's relevant to this conversation? Do they have extreme values? If I said, what's the maximum value of e to the x, what should you tell me? Yeah, well, technically at infinity, but that means we never get there. We don't have an absolute maximum. Does that make sense? Because it's increasing forever, so I can't find an absolute maximum, nor can I find an absolute minimum, right? I have a lower bound on it, but I don't have an absolute value. I can't go say, well, if you plug in this number, you're going to get the lowest value you'll ever get for it. Does that make sense? Unless I take a chunk of it out. Does that make sense? All right. Let's see if there's any other pictures I want to include here. I think that'll do it. So one of the morals of the story of this little conversation we just had, sort of to kind of let you know where we're going with this, is that when you start doing analysis, because there will be situations where you don't have a calculator and you may not be familiar with the graph. So we've already decided that the extreme values will occur at either the endpoints or at an extreme value in the interior, right? Well, what's going to happen is you're going to be so amped about the fact that it's all starting to come together, because what should happen in this chapter, if you've been working but struggling with some ideas, you start to iron out those wrinkles and it starts to make sense in the context of visual examples of what we're doing. You'll get so excited about the fact that you know how to find the extreme values and you know how to tell me whether they're maxes or mins without ever graphing it, that you'll forget to check the endpoints. And that's why I included these three little pictures here, because what situation you're in, you might not be able to visualize, but you'll be able to find the interior points, but don't forget to check the endpoints, and I'll reiterate that when we get to examples. All right, well, if we have globals, what else could we talk about? Locals, okay? So we're going to define now local extreme values. And I'm going to be bold here and call that EVs. All right, here's your preface. Let C be an interior point of the domain. Oh, that's terrible. Let me fix that. Interior point in the domain, and I'm going to use capital D for that, just to cut to the chase, of F. And F is a function. All right, so I'm going to save us some time with some of that very carefully worded definitions to get us to the meaning of it. All right, then, and since we've already talked about it on the other one, I can go ahead and throw that in here. F of C is A, and again, we're going to split off into two parts, and that should be obvious at this point while we're doing that. All right, and part A of those two parts is a local maximum value. We're going to abbreviate again. And this kind of bothers me, but I'm going to put it in here because it's actually in the dictionary. In the definition here, which is the dictionary definition. At C, why is at C redundant? Because the function notation told you that. Okay, and I don't know if that would bother you like it bothers me. All right, so then f of C is a local maximum value of, at C, if and only if. All right, what has to be true at a maximum? Okay, let me give you a hint. We're going to compare f of x to f of c. What is the distinction there? No, what's the distinction between the notation of the two things I just wrote, f of x and f of c? When I say f of x, what am I talking about? The entire function. When I talk about f of c, what am I talking about? A specific y value on the function, right? Now, I'm pointing out those little distinctions because that's another weak area for us. And I'm going to tell you something. I think as a class, y'all are probably doing better on that particular area than any class I've taught before. But there's still some holdouts, so I got to keep working with you on that. It is not okay to say that f prime of x equals f prime of 0, because that's not true, unless it's a line. Because a line, the slope is the same everywhere, right? So that's something we got to work on. Like I said, my demanding ways about the notation is paying off because y'all are doing better. And every year I push a little bit harder on that, and it's paying off. So we're gonna get everybody there. So what has to be true about the pairing of these two? So I'm gonna start the sentence off just to make sure our brains are in the right place. Then f of c is a local maximum value of c if and only if. What is true about these two? That's right. F of c has to be bigger than every other value on. But now we're talking about locals. On the domain would make it an absolute or global, right? But we're talking about a local. Right. Now, this is some specific wording here that you need to include because you're right. For all x in, now this is, it could not be more emphatically generalized here. In some open interval interval containing C. That's a pretty strong statement, isn't it? So what does that wording tell you? In some open interval containing C. That would be kind of like my telling you, you can turn homework in as long as you can name an interval containing the due date. My response would immediately be all time. Why would that take care of it? Because if I say all time, any moment or date I specify is in there, yes? Okay? But I could also specify an interval of give or take a day, right? That's a little tighter. You see what I'm saying? But if it just says in some interval, so if you can find an interval that contains that value, and the reason that matters is when you're applying the problem, you're like, I didn't even know I should have thought about that. But you're gonna have problems in this chapter where you're like, how are we supposed to know what to do? You got to think back to your theorems, and if it says on some interval, then if you can show that, well, I know that the function is negative between 1 and 4, so I know somewhere on that interval this happens. You see what I'm saying? You've just got to have some reference point in the problem that tells you what interval contains the value you're talking about so that you can make your statement definitively. And that's kind of abstract, so it's okay if it's not 100% clear. But I'm just kind of trying to plant some seeds here. All right, so that's our first part. So what's our second part? The local minimum value. And what is the extension of that part going to say? At C, if and only if, f of x is, and he says that with hesitation in his voice. Is he right? Greater than or equal to f of c? Yes, he is. I also want to emphasize that we're not saying it's greater than, it's or equal to. So like a few minutes ago I said name a value that has absolute maximum. and most of you, name the ones who contributed things. They were the more obvious ones. But why might sign make you scratch your head for a minute? Because Colin said that, and he is correct. But why might that mess with your head a little bit? Because how many times does it hit its maximum value? An infinite number of times. Okay, so that's a really good example to think about. So remember, or equal to takes care of it. Does that make sense? All right, so finish it out. So then f of c is a local minimum value at c if and only if f of x is greater than or equal to f of c. Exactly. You're going to end it just like you did the first one. For all x in some open interval. You don't see such general wording in math very often. In some open interval containing C. Now the wording here and the fact that that is as vague as it is means that 3 or 4 or 10 of you could have different intervals and you could all be correct. That's terrifying to some of you. You're like, what? Now, obviously, you'd have to reach the same conclusion about C, but the interval you use in your justification might be different. Okay? All right. The other name for, what's the other name for absolute extrema? Global. Okay? Global, absolute mean the same thing. All right? Local, and I'm just going to write this as an implication statement. And I'm going to do it as a two-way arrow because this is the same. In fact, let's just do it this way. Let's go back up and say global. I don't know why I capitalized that. It was just what my hand wanted to do at the moment. All right, global implies absolute, right? Local implies relative. Do y'all understand when people say, well, that's relative? What does that mean? Yeah, it depends on the situation you're applying it to, right? So, or like if I said the smartest kid here, that would be a relative reference, right? You see what I'm saying? Because that if I say you're the smartest kid here, I'm not saying, and today I of course would say it would be Sarah because she made 100 on my test, which doesn't happen very often. I should keep stats on such things so I can tell you how rarely that happens. But let's just say I just said Sarah is the smartest kid in this room because she made 100 yesterday. Nobody else has. All right? Well, does that mean that she's the smartest kid on the planet? No. So that's a relative reference. Does that make sense? It's relative to the context of what I said. Does that make sense? Okay. That matters because the word is going to come up often enough that you're going to be like, wait, I thought it was the other word. It depends. All right. Theorem 2. We're getting to the good stuff. And I'm trying to take time on the more basic stuff so that all the big stuff will make more sense, okay? Local extreme values. Again, I'm abbreviating to reinforce the notion that we can all use this verbiage. Well, let's pause for a minute. Now, I asked you, and I even left the room to give you ample time to discuss before we actually started our notes today, to discuss what you know about extreme values. Okay? But what I heard a lot of pre-cal knowledge, but I didn't hear anybody, and you might have talked about it, it just didn't come up in our group, our whole class conversation, but I didn't hear anybody say anything about calculus. And I'm so thankful I don't have a video who goes, well, in calculus, and then tell me something pre-cal. All right. Well, what do we know about the calculus of maximums and mins? Well, what is the calculus you know so far? It's a D word. Derivative. What do we know about the derivative at extreme values?
Zero.
What 0? The derivative there equals 0. Which does, you did say that? She didn't mean for me to hear that, people watching the video. That's hurtful. Okay, your derivative is 0 there. And why does that make sense in the context of the pre-cal discussion we had about it? Because what happens, in order, let's just say it's a maximum. If I have some kind of maximum, what has to be true? It has to be increasing to the left of it and decreasing to the right of that point, right? Okay, well, what does that say about my derivative on the left? Be positive, and then on the right side would be negative, and you can't get from positive to negative without being 0 in between. Doesn't that make sense? Okay. So theorem 2 says local extreme values, and you'll understand why I stopped and did that little preceding comment when we write this. So here's what this theorem says. And you should love these theorems because you're going to put them into practice on practically every problem you do in this chapter so that they're going to become obvious to you as you go. It won't even feel like a theorem anymore. You remember having those in geometry where you're like, really, we need a theorem that says this? Yeah. I'm sorry, I didn't mean to bring up any latent trauma. All right, if a function, in fact, I'm not even going to say that. I'm just going to say if f. Are we okay with saying f is a function? Okay. If f has a local, and your definition or your wording of the theorem itself says it has a local maximum value or local minimum value, we're going to say max / min, because I think your generation reads that as one or the other. Yes? Okay? So if f has a local max or min at an interior point, get your brains ready because I'm going to ask you a question in a minute. C, and universally in this chapter, that point of interest will be called C. And this almost bothers me to write it, but I'm gonna shortcut it and say of capital D, which means the C is somewhere on its domain, right? Okay. Comma. And if f prime exists at C, then what do we know has to be true? Write it on your paper. And I'm going to write it and see if you're right. And I'm going to write it really big to emphasize it. It's not like I've lost track of the board. I'm doing this on purpose. Ready? I'll give you a hint. The first thing you should write is an F. And then a prime. And then at C equals 0. Feels good, doesn't it, to know what you're doing? All right. And there's a lot of notes in this particular section. We're almost finished. We're almost to the finish line. But it's almost like this is the lesson where you learn the language. Okay? And then we won't have as much tedium in future lessons. All right? So if you have a friend who is not present today, as in particularly our junior leaders who should be back tomorrow, you should advise them to, whatever else they do, watch the video before they come to class tomorrow. Okay? Because if we run out of time with examples, which we might, then I will pick up with whatever we left off with today. All right, definition, critical point. Oh, I forgot my question. Let me back up to my other screen and ask it. See, it's funny because I heard both groans and enthusiasm. Oh, no. All right, now let's talk about this theorem for a split second because it's pretty straightforward and it fits with everything we already knew, doesn't it? What have I told you since the day I met you? If math doesn't fit with everything you know, you're not understanding it right. Okay? Unless you start heading off into some kind of quantum theory or something. That's a whole new world, so that's a different context. All right? If f has a local max or min at an interior point C of the domain, and if f prime exists at C, then f prime of C equals 0. Why, in that statement, is the at an interior point C important? Because y'all said we're taking a derivative at a point. Is that what you said? Okay, let me zoom you in even farther. Why does the word interior become everything to this theorem?
There can be multiple ones, and it's on
Wait. Ooh. Thought I was gonna have to back up to get you there. Say that louder, Aaron.
It's an endpoint, the derivative will be 0.
That's exactly right. I was gonna take you back to the closed interval part we talked about at length. Because what did we decide about a closed interval? What did we decide about a closed interval, Will?
Close interval.
Oh, I love the stalling tactics. Y'all think you're so smooth. No, that might work with your parents. It doesn't faze me.
Yeah. It's
Oh my God. What did we say about a closed interval? Well, let's rewind. What are we talking about today in this lesson? Maxes and mins, extreme values, right? Okay. Why is the discussion of whether you're asking me about a closed interval or an entire function important to know? Because I demonstrated for you, look back at those little sketches I gave you with the closed interval reference and go back to the chunk of the exponential. What did we agree about exponential functions? They have no maxes nor mins as a function, right? Because all exponential functions either increase everywhere or decrease everywhere. Which means the same, and I'm going to say this, and then I hope somebody can pick up where I'm leaving off. Which means that the same thinking can be applied to what class of functions? Logs. Why? Because they're the inverses of the exponentials. And how does that work graphically? If I've got an exponential function, how do I get its inverse? I flip it over the line y equals x, which gives you the same graph relative to the x-axis that you had to the y-axis. Does that make sense? Okay? So all of this needs to make sense because that needs to be almost subliminal in your processing when you're doing these problems, because there are problems that are going to push you to understand that personally, individually. So that's where you need to feed back on your pre-calc knowledge. Does that make sense? All right, so the word interior here becomes important because, as Aaron so wisely said, if I have a closed interval and you look at any of those little sections I gave you to look at, the endpoint, if I plug the derivative in, I'm going to get some number other than 0, right? Because the function doesn't know that you've cut it off there, right? So it's not going to have, it's not a natural, and to me endpoint maxes and mins are what I call not natural. A natural one when I say that, I mean like an interior point that you know is a regular function behavior thing. Does that make sense? And that's just my little reference to it. All right, critical point. And that needs to be clear before we talk about a critical point. A critical point is a point, I know, that's shocking, isn't it? In the interior. Crazy that a critical point would actually be one. At the interior, or in the interior of capital D, what is that? Domain. The domain of a function, which I'm going to abbreviate FCN, as will your college professors, and that is distinguished from function f, because when we say function f, we're talking about some particular function, but when we say of a function, we're talking about just functions in general, at which f prime equals 0 or f prime DNE. What does that mean? Does not exist.
You said or above.
I'm so sorry. I'm translating the definition and processing a phrase ahead of what I'm writing. Not a good thing to do on this early morning. Or is the word I meant to write there. Or, and I guess I was thinking of writing the f after that. F prime does not exist, and I was also trying to decide if I had room to get that in there. That's why this format is not ideal for me, because it distracts me. A point in the interior of the domain of a function at which f prime equals 0 or f prime does not exist. And we can actually stop there because that tells you what the definition is. That's a critical point. And we have to know that. I mean, and again, I can't emphasize enough that everything I teach you, you have to know, or I wouldn't be teaching you. Okay? All right. So, a point in the interior of the domain of a function at which f prime equals 0 or f prime does not exist. So in other words, if I hand you a function and I tell you to find all the critical points on the function, this is how you find them. So what would be your first step? Take the derivative, right? Yeah? And then look for what? Horizontal and vertical tangents, i.e. set your derivative equal to 0, solve for x, or look for places where you have a vertical tangent, where your slope is undefined. In other words, how do I tell that when I look at my slope? How do I decide where my derivative is undefined? Talk amongst yourselves for about 30, 45 seconds. Because you should know this. Have we decided? Wow. Thank you so much for overwhelming me with your response. Okay, my question was, how could I tell? Because here's what happens. Y'all tell me, I don't know what I'm supposed to do next, because you're not thinking. You cannot be successful at completing calculus problems unless and until you learn to actually think about everything you're doing. And in order to be able to think about what I'm doing, I must first understand. Which is why you have set yourself up for failure when you don't understand and you don't ask. And you say, well, I asked my classmate who has a degree in math from what university? Oh, wait, that's Twitty or Matthews. Right? Now, you could ask some of the other math teachers, but they may or may not remember their calculus because it's probably been a while since they've thought about calculus. Okay? So I'm going to ask you again. If I give you a function and I tell you to find the critical points, what are you going to do? And the first part's easy, right? I'm going to set my derivative equal to 0 and solve for x. That would tell me where I have a horizontal tangent. How do I determine whether I have vertical tangents from my derivative? Where the denominator equals 0, right? Because in essence, that is how you do it, right? But what if, let's say my derivative was 3x squared. Where does that have a vertical tangent? What's the denominator of 3x squared? 1. So let me ask that again. Where would it have a vertical tangent? Nowhere. And see, some of y'all think you can kind of zone out and check out because you're not comfortable speaking in the class, but your problem with that is that you don't get your misconceptions clarified, not to mention the fact that if you're one of those people, you probably have a separate track running in your brain the entire time I'm up here saying things like, oh God, you really screwed up on that test. How are you going to explain that to your parents? They're never going to let me do this, this, and this because my grade has not come up since my interim. I mean, am I right? We've all been there. I was doing it yesterday. Guilty. PL Tuesday. There was probably 90% of the time I was there that I was not focused on what was happening around me. And then I realized it was more of a summary type checklist thing. I was like, oh, maybe I should pay attention. So I did. That's what you should do every day in here. And I'm only saying this because I graded your test last night. Okay. So that takes care of the critical point. And this is the first textbook I've actually seen stationary point in, and I don't know if this is a word that's becoming more utilized out in the math world, so I'm going to include it just in case it comes up in the context of your exam or otherwise. All right? A stationary point is, and I'm going to start writing beside it because I think I'm going to squeeze in a little room here. A point at which, or not, well, I got to go all this little specificity here. A point in the interior of the domain, so I'm going to put D, of a function at which f prime equals 0, period. Now, I put these all on one screen, and I wanted to make sure you had clarity on what a critical point was before I wrote the definition of the stationary point, so that you could have them there together to compare. And what occurs to you as you read those two definitions side by side? Okay. There is definitely a connection between these two terms, right? Okay. This is one of those pairs of terms that your English teacher might ask you to write a statement that if a point is a blank point, it is also a blank point, and have you put the right words in the right places. What matches up in these two? Okay, so how do I get to be a stationary point? The first requirement for both of them is that we're talking about the interior of the domain. So like if I was talking about the square root graph, what is the only point on the square root graph where I'm not in the interior of the domain? At the origin, right? Because that's a graph, that is a parent function with an endpoint, right? The function is defined from that point forward and not to the left of it. So any other point on the square root graph would work. All right, so a point in the interior, on the stationary point, a point in the interior of domain is where, what happens? F prime equals 0. So for the square root graph, could I have a stationary point? Why? That is exactly right. Because what do I know from a pre-cal perspective about the square root graph that makes it impossible to have a stationary point? It increases everywhere. Right? So if it's increasing everywhere, it can't have f prime equals 0 because the derivative would have to change signs, right? Okay, now let's come back to the critical point. There's an or in the critical point definition. What's the other possibility to be a critical point? So if I say to you, all critical points are also stationary, true or false? False. Got it? Sweet, let's do some examples.
Was that VS like a versus thing? Or what did VS mean?
VS? What does VS mean? It means versus. As opposed to. Your mother's an attorney and you don't know what VS means? My God, go talk to Anne.
Yeah, that's what I asked.
If anyone ever writes VS on the board that way, that's what they mean.
I just wanted to make sure.
Okay, that's cute. Not quite as cute as your haircut, but cute. Now you can open your books, please, to page 198. And we're going to start with what in my mind should be really simple examples, because I want you to see that some of this can sneak up on you and you can think you understand, and then you're handed a graph and you're like, oh, wait a minute, and the whole point of those problems is to define and then refine your thinking about all this stuff. Okay? Are y'all with me on page 198? And the reason I want you there is that we're going to talk about 1 through 10 before we do anything else. Okay? So, I'm going to pause the video for a second. Okay, for my video people, I paused the video to give your classmates an opportunity to see what they thought about number 2 on page 198. And if you would pause the video and do the same for yourselves right now, that would be great. Talk to me about number 2. What do you think? First of all, and this is sort of a mental checklist, and I'm big on talking to you about mental checklists because of the fact that no one before you met me apparently has talked to you about how to learn to think. Okay? The more you organize your thinking, and the people that you think are smarter than you are just either had some influence in their environment or they just had a genetic predisposition to need to organize things in their brain, because that's how you think. You have to, it's almost like you have to file what you're learning in the context of what you already know, all right? So when I approach this problem, the first thing I should do is ask myself, do I have, and I'm really asking you right now, do I have in this graph for number 2? And again, another little thing you need to know for the rest of your education and really for the rest of your life, you can only take the information that's presented to you. You can't make assumptions or guesstimates about anything else. This is the whole function, okay? So, does in number 2 there appear to be an absolute maximum or minimum? I heard yes and no.
No, because it's endpoints.
Okay, what would it require to be an absolute or global? Where's Brian when I need him to answer my phone? I'm not Brian, I'm sorry, Carlos. God, that was a flashback. Yes, ma'am? Okay. All right. Okay. That's what she just called you. Miss Huff said that when you leave here, go to guidance. Shatia. She called you Shatay. That's what I'm saying. Miss Huff, she's the lady at the desk. Guidance. Go to guidance when you leave here. For the FMU people are here. Francis Marion? Well, you're next in line, so they must have compressed the schedule. I don't know what to tell you. I'm just the secretary. Okay. So, now that our video has completely been disrupted, I was in the process of hearing your thoughts on whether or not our function in number 2 has an absolute minimum or maximum. And if you believe it does, please raise your hand. That's a good sign that no one... Oh, there was a hand coming up. Hannah, talk to me about that. Okay, what's required to be an absolute? It has to be... But the definition is all I'm asking you. What is the definition of an absolute maximum? Absolute or global, which was the very first definition we wrote.
If and only if f(x) is less than or equal to.
Okay, if and only if f of x is less than or equal to f of c in its domain. In other words, everywhere, right? So when you read that phrase, in its domain, you mean on the entire function. This is the point that the graph goes as high as it can. Where would you like to say in that picture you have such a creature? At 1? At 0?
It's at 0. The point's at 0.
What is the function value at 0 on this function? 0. You want it to be up there at the top, right? But what's at the top? An open endpoint of a segment, right? Which means the function is not defined there, it's defined at 0. But even if that point wasn't there, take the point, the fact that they've got the function defined to be 0 at 0, take that out of the picture. You still don't have an absolute maximum or a minimum. Why? Because what happens at an endpoint?
There's
At an open endpoint.
the derivative.
Q gets infinitely close to that.
That's exactly right. You can get as close as you want to, and I can get closer. We could leapfrog forever, right? Because we could go in little tiny increments, but we'd never get there. So we can't ever say there's an absolute maximum value, because you could say, well, to me, the absolute maximum value is 1.99. And I'll say, well, how about 1.999? And then you'll say, well, what about 1.9999? You with me? That's the problem. So if the top point in the picture that's marked is an open point, that means we don't have an absolute maximum. By the same logic, then, we do not have an absolute minimum. Are y'all with me on this picture? Okay? Do I have relative? And notice the directions don't specify. It just says extreme values. So when you find them, you need to classify them as either absolute or local. All right? Do we have extreme values in this picture? Where? No, this is not a trick question. At 1, 0. What do I have at 1, 0? I have a local maximum. Because on some interval containing C, and what's my C here? 1. It's the highest point. So it's a local maximum. Does that make sense? You see how this picture forces you to get clarity on what your abstract ideas were? Will?
Okay, so like if you were gonna write that, would you have to write your interval, your
No, that's how you would defend it.
You just write local max.
Yeah, exactly. There's a local maximum for this function of, what is my local maximum there?
1, 0.
That's the point where something happens. That's not what happens. 0. I have a local maximum of 0 when x equals 1. Not a trick question. Y'all all look at me like I'm speaking some sort of strange language. All right, so if I have that at 1, what do I have at -1?
Local.
A local minimum by the same logic, right? Okay, now let's talk about number 4. Okay, well let's record those answers. So we have, for number 2, we have a local min of 0 at x equals -1. And that's how you should write your answers. And I still have a few holdouts, and I'm making progress. As a group, you're doing a lot better on this, but there's still some of you who are stubborn and or don't believe in yourself enough to actually apply the things I tell you. But if you don't write this way on your homework, you won't do it on your test. Just like if you don't learn how to be a student here, you won't be one when you get to college. I've had so many seniors tell me that over the years. I'm gonna do it when I get to college. No, you're not. You're not. You're gonna go to college and do exactly what you've done here and see how that works out for you. All right, and we have a local max of 0 at x equals 1. Yes? Okay. So now let's go to 4 and start there tomorrow.